Tonight, we're going to look at Mars region by region, crossing a planet whose day feels almost familiar while nearly everything in its environment is not. At the surface, the air presses with only about 6 millibars. It is a pressure more at home high in Earth's stratosphere than beside any earthly sea. The air is mostly carbon dioxide. The planet has no global magnetic field, no open water, and no place where an unprotected person could wait beneath the sky until morning. A Martian solar day lasts 24 hours and 39 minutes. Sunset arrives. Darkness moves across plains, craters, volcanoes, and canyons at a rhythm the human body would nearly recognize. That familiar clock makes Mars especially deceptive. A night is not an abstract span lasting months or years. It is one evening, one midnight, and one dawn. Yet the cold deepens quickly. Radiation continues to cross the thin air, and the atmosphere never becomes dense enough to breathe or to hold pressure around the body. But which boundary would end an unprotected human life first? The missing oxygen, the missing pressure, the cold, or the radiation? The honest answer begins with pressure and oxygen, then grows more complicated as the hours pass. The exact order matters less than the central fact. Mars does not offer a single fatal obstacle. It offers several, layered together, and every successful habitat must replace the planetary systems that Earth provides without being noticed. By the end of tonight, you're going to understand exactly how Mars changes from its young northern plains to its ancient southern highlands, why regions such as Jezero, Gale, Valles Marineris, Tharsis, and the polar caps are so different, and why none of those differences creates a naturally safe night for a human being. We will also look at what a pressurized habitat would have to do, hour after hour, to turn that impossible night into an engineered one. Before we get started, if you love exploring Mars as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first step is to stop thinking of Mars as a uniform red sphere. Orbital maps reveal a world divided by altitude, age, rock type, ice, dust, and the scars of impacts. The most obvious division runs around much of the planet. Broad northern plains lie several kilometers below the rougher southern highlands. Volcanoes rise above that pattern. Impact basins cut into it. A canyon system crosses the equatorial region for nearly 4,000 kilometers. Each region records a different chapter of planetary history. Those differences shape local weather and exploration. Air pressure is higher at the floor of a deep basin than on the summit of a volcano because more of the thin atmosphere lies overhead. Temperature changes with latitude, elevation, season, surface color, and time of day. Dust settles in some hollows and is swept from some slopes. Water ice comes close to the surface in many high-latitude locations. Ancient lake sediments survive in craters where rivers once slowed and deposited mud. Yet geography does not overturn the basic survival limits. The deepest accessible basin does not contain breathable air. The warmest equatorial afternoon does not continue through the night. A patch of subsurface ice is not a spring. A low radiation interval is not a permanent shield. Mars can give an explorer more favorable versions of dangerous conditions, but it does not supply the complete environmental package that an unprotected human body requires. Our route will move as a planetary survey rather than a straight walk. We begin with the globe itself, then descend into the atmosphere. From there, we cross the northern lowlands through Utopia and Elysium, turn toward Jezero and the ancient transition zone, enter the southern highlands, climb the layered record in Gale, follow Valles Marineris westward, rise onto Tharsis, and finish at both poles before returning to the problem of a single night. Imagine the map not as a collection of tourist destinations, but as a diagram of systems. Contour lines describe pressure, Latitude describes sunlight. Crater walls preserve old rock. Dunes describe wind. Polar layers record climate. Rover tracks show where machines can function for years under careful thermal and electrical management. The map is beautiful, but it is also practical. Every named region asks the same quiet question in a different physical setting. What must a traveler bring that the planet itself will not provide? Mars is smaller than Earth, though, not small by human standards. Its radius is about 3,390 kilometers, a little more than half Earth's. Because a sphere's surface depends on the square of its radius, the total Martian surface is close in area to all the dry land on Earth. A world with the land area of our continents can therefore fit inside a globe only about half as wide as Earth. The result is a planet at once compact and geographically immense. Average distance from the Sun is about 228 million kilometers, or 1.5 astronomical units. Sunlight needs roughly 13 minutes to travel from the Sun to Mars. The Sun appears smaller in the Martian sky, and Mars receives less solar energy per square meter than Earth. Solar power remains useful, as the history of landers and rovers demonstrates, but the energy budget is tighter, and airborne dust can make it tighter still. The Martian rotation is one of the planet's most familiar properties. One sol lasts 24.6 hours. A clock designed around an earthly day needs only a modest adjustment. Mission teams on Earth have sometimes lived on Mars time during critical operations, allowing their work schedule to slide by about 39 minutes each day. The human sense of morning and evening could survive that shift. The human body exposed to the Martian environment could not. The year is less familiar. Mars completes an orbit in about 687 Earth days, or 669.6 sols. Its axis tilts about 25 degrees, close to Earth's 23.4 degrees, so the planet has seasons, but its orbit is more elliptical, and the seasons are unequal. Northern spring lasts about 194 sols, while northern autumn lasts about 142. Seasonal changes in sunlight interact with carbon dioxide frost, water ice, winds, and dust across the globe. Gravity at the surface is about 0.375 times Earth's. A person with a mass of 80 kilograms keeps the same mass but would press on a scale with only about 30 kilograms of Earth equivalent weight. Walking, lifting, and falling would all feel different. No one yet knows every long-term biological consequence of living at this gravity, because humans have experienced sustained life at 1 gravity or near zero, not at 3/8 gravity. Even here, the apparently gentle number opens another unanswered requirement for settlement. The atmosphere is the first planetary system a visitor would notice through instruments, and the first one the body could not use. Near the Martian datum, surface pressure is commonly around 6 to 10 millibars. Earth's average sea level pressure is a little over 1,000 millibars. Mars therefore provides less than 1% of the pressure familiar at sea level, with local values changing according to altitude, weather, and season. Composition makes that thin air unusable, even if pressure were higher. The InSight mission's reference figures describe an atmosphere about 95.3% carbon dioxide, 2.7% nitrogen, and 1.6% argon, with only small traces of other gases. Oxygen exists only in trace amounts. A human lung cannot extract a useful breath from it. Breathing harder changes nothing, because the required oxygen molecules are not present in anything close to the necessary concentration. At the surface, the air presses with only about 6 millibars. That number explains several features at once. Liquid water exposed to the surface is unstable over long periods. Heat moves differently because there are far fewer gas molecules to carry it. Sound travels as microphones on Mars have demonstrated, but with different attenuation and speed. Parachutes work during entry, yet the thin atmosphere cannot slow a heavy spacecraft enough by itself. Rockets, airbags, or powered flight complete the landing. The atmosphere also rises and falls with the seasons in a way that has no close everyday counterpart on Earth. Carbon dioxide freezes onto a winter polar cap and later returns to gas. Mars Reconnaissance Orbiter results show that surface pressure can vary by as much as roughly 30% across the seasonal cycle. A habitat designed for one time of year must still tolerate the external changes of another, even though the interior pressure remains set by human needs. Wind is a useful reminder that pressure and motion are different things. Martian gusts can move dust, carve ripples, and build dunes. They can sound forceful through a lander's sensors, but the low density means a given wind speed carries far less force than the same speed at sea level on Earth. Cinema often gives Mars a storm capable of throwing a person across the ground. The real danger is quieter: obscured sunlight, dust intrusion, abrasion, thermal change, and a world of moving air that still cannot support one breath. Pressure and oxygen form the first survival boundary. Human tissues evolved inside an atmosphere that pushes inward while fluids and gases push outward. A pressure suit or habitat maintains that balance and supplies oxygen at a controlled partial pressure. Mars supplies neither. An unprotected person would face severe hypoxia and decompression, not a slow evening of increasing discomfort. There is no scientifically useful reason to assign an exact countdown because individual conditions vary, and no ethical experiment reproduces exposure on Mars. The careful statement is enough. Conscious human activity requires oxygenated gas at adequate pressure. Present-day Mars offers a near vacuum by terrestrial standards and almost no oxygen. The person could not remain alert, walk towards shelter, and watch the sky darken for hours. Loss of useful function would arrive long before the coldest part of the night and long before radiation accumulated into the main immediate problem. Temperature complicates the image but does not replace it. Popular descriptions sometimes imagine a body freezing instantly. Mars is cold, yet its thin air carries heat poorly. Direct contact with the ground, radiative heat loss to the sky, breathing, suit leakage, and evaporative cooling all matter. In a real emergency, decompression and oxygen deprivation dominate first. Cold becomes decisive across longer exposure, especially as the surface and equipment lose stored daytime heat. A spacesuit is therefore a small spacecraft shaped around one person. It holds pressure, meters oxygen, removes carbon dioxide and water vapor, controls temperature, blocks some radiation, manages waste heat, permits movement, and keeps dust away from vulnerable layers and seals. Every joint has to bend without leaking. Every glove has to preserve enough touch for work. Every connection to a rover or habitat has to survive repeated use in a dusty environment. This is why the phrase "survive a night" needs a boundary around it. A human could survive inside a functioning Mars habitat. The planet does not make that impossible. What the planet makes impossible is an unprotected night on the surface. Survival is transferred from environment to machine. The room must become the atmosphere. Its walls must become the pressure gradient, the thermal blanket, the dust barrier, and part of the radiation shield. Outside those walls, the first minutes remain governed by missing air. Mars is often summarized by a single average temperature, but a single average hides the structure of the day. The InSight reference gives a mean surface temperature near -53 degrees Celsius, with conditions ranging far lower during polar night and rising above freezing at favorable equatorial midday locations near perihelion. A global NASA summary gives rare extremes from about 20 degrees Celsius down to roughly -153 degrees. Both statements describe a world with sharp variation. At Jezero crater, Perseverance's weather instruments have measured typical surface temperatures rising from around -83 degrees Celsius before dawn to about 5 degrees at noon during the reported period. Air temperatures remained lower. The ground absorbs sunlight efficiently, while the thin atmosphere stores little heat. A person's boots could therefore face a surface much warmer than the gas around the helmet. The vertical contrast begins within the height of a human body. After sunset, the direction reverses quickly. The ground radiates energy into the sky. Dense terrestrial air and water vapor slow nighttime cooling, while oceans and vegetation store and redistribute heat. Mars has no ocean, almost no atmospheric mass, and little water vapor. The surface that warmed beneath the afternoon sun can lose that warmth rapidly. By pre-dawn, rover heaters and insulation have been working through hours of falling temperature. Different regions alter the curve. A dark rock absorbs more sunlight than bright dust. A deep basin has somewhat more atmosphere overhead than a high volcanic summit. A slope facing the afternoon sun remains illuminated longer than a floor already in shadow. Polar winter removes sunlight for extended periods, yet none of these places maintains a naturally habitable range through the complete sol. Local warmth is temporary and incomplete. Planetary scientists describe part of this behavior through thermal inertia, a measure of how slowly a material changes temperature. Solid rock tends to retain daytime heat longer than loose fine dust. Sand, bedrock, and dust can therefore sit near one another while following different temperature curves. Orbiters use nighttime infrared observations to help distinguish those surfaces. A landing site is not assigned one temperature. It is mapped as a field of materials that warm and cool at different rates. For a habitat, temperature control is not simply a furnace. Electronics produce heat. People produce heat. Batteries and life support systems have their own operating ranges. Insulation must reduce loss during darkness without trapping too much heat during active periods. Radiators must reject waste energy while avoiding dust accumulation. A failed heater in an earthly house is serious. A failed thermal system on Mars occurs beyond an exterior atmosphere that cannot be brought indoors, beside a landscape that continues cooling toward dawn. The next boundary arrives from above and from every direction. Earth protects its surface with a thick atmosphere and a global magnetic field. The atmosphere absorbs and scatters much of the incoming energetic radiation. The magnetic field redirects many charged particles carried by the solar wind. Mars has neither defense and terrestrial strength. Its atmosphere is thin, and the planet has no global magnetic field today. There are magnetic remnants. Spacecraft have mapped strongly magnetized sections of ancient southern crust, evidence that early Mars once possessed a planetary dynamo. Those patches can create local magnetic structures high above the ground, but they do not wrap the world in a continuous shield. Their presence is a record of something Mars lost, not a surface refuge where an unprotected person can stand safely. Curiosity's radiation assessment detector measured the environment at Gale crater from August 2012 through June 2013. The average dose from galactic cosmic rays and solar energetic particles was about 0.67 millisieverts per day during that interval. More than 95% of the measured total came from galactic cosmic rays, and the period did not include a major solar storm at Mars. The value changes with solar activity, altitude, atmosphere, and shielding, so it is an observed interval rather than a universal constant. Radiation is not the first thing that defeats an unprotected person during a brief exposure. Missing pressure and oxygen act much faster. Radiation matters because a human expedition is not one brief exposure. Transit to Mars, months on the surface, and the return flight add together. using the cruise and surface measurements for the same part of the solar cycle. The Curiosity team projected a round-trip mission dose on the order of 1,000 millisieverts. That is an engineering and health problem measured across the mission. Shielding changes the architecture of every safe night. A habitat can cover living areas with water, supplies, or Martian material. It can place sleeping quarters below grade or inside a naturally shielded site after careful study. Space weather monitoring can move a crew into a more protected compartment during a solar event. The method may vary, but the principle does not. Mars gives the traveler a sky. It does not give the traveler Earth's invisible protection beneath it. Mars is red because iron-bearing minerals in its rocks and regolith have oxidized. The planet seen from space is also shaped by particles fine enough to remain suspended in the sparse atmosphere. Dust softens distant horizons, colors the sky, coats solar panels, enters mechanical joints, and records wind direction in ripples and streaks. It is not background decoration. It is a mobile part of the climate and a persistent part of the surface engineering. Fine grains create problems at several scales. A film on a solar array reduces the light reaching its cells. Material in a seal can create wear or a leak path. Particles on a visor scatter light. Dust transferred into a habitat can reach filters, fans, electronics, skin, and lungs. NASA Materials experiments on Perseverance exposed pieces of space chute-related fabrics and helmet visor material to the real surface environment because ultraviolet radiation, dust, and cold act together over time. The chemistry adds another layer. The Phoenix lander found perchlorate salts in northern soil, and later missions found chlorine and oxygen-bearing compounds consistent with perchlorates elsewhere. NASA research treats these oxidizing salts as a resource processing and health concern. The point is not that touching one grain ends a mission. The point is that a settlement cannot assume local soil or extracted water is automatically safe for breathing spaces, food systems, or drinking. Material must be characterized and treated. Dust control begins outside. Suit ports could keep most of a suit beyond the pressure wall. Brushes, electrostatic methods, covers, replaceable seals, and staged airlocks can reduce transfer. Inside, filtration has to work continuously, and components must remain serviceable. The design cannot rely on a perfect barrier because people move, tools return, samples enter, and every opening creates another route for particles. At night, dust also changes energy. Suspended particles reduce sunlight during the day and alter how heat moves through the atmosphere after dark. A regional or global storm can cut solar production while daily power demand continues. Batteries, stored energy, or another dependable source must carry life support through the interval. Mars dust is gentle enough to hang in 6 millibars of air and consequential enough to reach almost every system built against that air. With the environmental limits established, the geographic journey begins at the largest pattern on the map. Mars has 2 broad provinces. Much of the southern hemisphere is high, rough, densely cratered, and geologically old. Much of the north is low, smooth, more lightly cratered, and resurfaced by younger deposits and lava. The boundary between them bends around the planet in scarps, slopes, mesas, and broken terrain. The difference in mean elevation is several kilometers. Early global analyses placed much of the northern lowlands about 3 kilometers below the highlands. The transition can spread across hundreds of kilometers rather than forming one simple cliff. Volcanic regions such as Tharsis and Elysium interrupt the pattern, and huge impact basins create exceptions in the south. A map simplified into north and south is useful, but the real boundary has coves, promontories, buried sections, and complicated local histories. The cause remains unresolved. A very large impact early in Martian history is one proposed explanation. Internal processes that created different crustal thicknesses are another family of ideas. Later erosion, volcanism, deposition, and impacts modified whatever original boundary formed. The terrain preserves the result more clearly than the origin. Good planetary science keeps those two levels separate. The dichotomy is observed, while its birth is still interpreted. This division matters to a traveler. Lower elevations usually carry somewhat greater atmospheric pressure because the column of gas above them is deeper. Smooth plains can offer safer landing zones than boulder fields or steep highlands. Buried ice may be accessible in some northern regions. Ancient southern rocks may preserve a longer geological record. No one site is best for every purpose. Landing safety, science, water, power, communication, and ascent all pull site selection in different directions. The dichotomy also changes the story of Mars from a sequence into a contrast. To the north, broad plains hide much of the oldest surface beneath younger material. To the south, cratered highlands retain impacts from early solar system history. Between them lie deltas, valleys, and eroded remnants that record material moving downhill. Region by region, Mars is a world where altitude is history written vertically. Utopia Planitia occupies a vast part of the northern lowlands. The name means a plain, and from a lander's height, the landscape can look modest. Scattered rocks, patterned ground, a low horizon, and an open sky. Viking 2 landed there in September 1976, returning a view whose quietness helped define the public image of the Martian surface. Decades later, orbital instruments revealed far more structure beneath and across the plain. Utopia is widely interpreted as an enormous impact basin buried and modified by later deposits. Polygonal patterns appear across parts of the surface produced by cracking and changing ground conditions. Lobate forms, mantling deposits, and subsurface signals point to a history involving ice. A plain is not an empty sheet. It is a layered record whose largest structure can disappear beneath the smoothness of its later surface. For exploration, the appeal is clear. Low relief can reduce landing hazards. Northern latitude and subsurface ice can make local resources relevant. The lower elevation provides more atmosphere above the site than a high plateau, which slightly helps entry and raises outside pressure. But slightly is the important word. At the surface, the air presses with only about 6 millibars near the global reference level, and local gains do not turn the atmosphere into a breathable one. The Viking 2 sunrise shows the Martian sky brightening around a small sun. Dust and ice particles scatter the light. Near the sun's position, blue wavelengths can be emphasized even while the wider sky remains dusty and warm-toned. A person inside a protected window could recognize the event as dawn. Outside, the atmosphere producing that delicate glow would still be almost 200 times too thin compared with Earth's sea level pressure. Utopia therefore demonstrates the distinction between favorable terrain and a favorable environment. A flat place can be easier for a spacecraft. Ice can be useful. A low basin can offer more gas for aerodynamic braking. None of those properties supplies open-air human survival. The plain may become a good place to build precisely because every missing service can be brought, manufactured, stored, and shielded there. The safety would belong to the built system, not to the horizon. West and south from Utopia lies another broad lowland province, Elysium Planitia. It sits beside the Elysium volcanic rise and includes surfaces shaped by lava, wind, impacts, and tectonic fracture. NASA chose a smooth area in western Elysium for the InSight lander, not because the visible rocks were the most varied on Mars, but because a level, safe site served a mission listening to the deep planet. InSight landed on November 26, 2018, near 4.5 degrees north latitude. Its purpose was to take what the mission called the vital signs of Mars: seismic activity, interior heat, and the planet's subtle rotational behavior. The lander's robotic arm placed a seismometer directly on the ground and covered it with a wind and thermal shield. That small protected instrument became a model of the larger human problem. To hear Mars clearly, it first had to be isolated from Mars weather. The plane can appear nearly featureless at human scale, but the instrument recorded movement passing through crust, mantle, and core. Seismic waves changed speed and direction as they crossed materials with different properties. From one station, the mission constrained the thickness and structure of the crust, investigated the mantle, and measured a core larger and less dense than some permission estimates. An apparently quiet site opened a cross-section through the planet. Elysium's daytime environment also changes rapidly. Convective turbulence can lift dust and create devils. Wind vibrates lander structures. Temperature falls after sunset, changing materials and background noise. InSight engineers protected the seismometer because signals measured in fractions of ground motion had to be separated from the ordinary pressure and thermal cycle above it. That protection had layers. The instrument itself included an evacuated enclosure and thermal barriers. The dome placed above it blocked much of the wind and reduced rapid temperature effects. Engineers also studied vibrations from the lander, the tether, and weather. Detecting a quake was never a matter of hearing one obvious sound. It was a matter of identifying a coherent signal after each known source of local noise had been measured or reduced. A human habitat in Elysium would use the same logic at a different scale. Select smooth ground, anchor equipment, isolate sensitive systems, watch dust and wind, manage a long thermal cycle, keep the internal pressure independent of the external 6 to 10 millibar weather. Elysium seems quiet because its motions are subtle, not because the world has stopped. Under the plane, stresses continue to gather and release. The strongest cluster of well-located marsquakes detected by InSight came from Cerberus Fossae, a set of long fractures east of the lander. Orbital images show steep-sided troughs cutting young volcanic plains. The region contains evidence of volcanism within roughly the last 2 million years, very recent compared with the age of a planet formed about 4.5 billion years ago. Mars is quieter than Earth, but quiet is not the same as geologically finished. Across 4 years, InSight measured more than 1,300 seismic events. More than 50 carried signals clear enough for scientists to derive useful location information, and the largest group of high-quality events pointed towards Cerberus Fossae. Some marsquakes arise as the planet cools and contracts, allowing stress to fracture rock. Meteoroid impacts provide another source. The data distinguish a living geologic record from a world frozen into complete stillness. Mars does not operate with Earth's global system of moving tectonic plates. On Earth, plate boundaries organize most earthquakes and volcanoes into connected belts. Mars instead preserves enormous volcanic provinces and localized fractures on a planet whose outer shell behaves differently. Cerberus Fossae is important because it shows activity concentrated without an Earth-like plate boundary, and because its young lava surfaces narrow the time since some eruptions. For a future settlement, the seismic hazard would be studied rather than assumed. A slight quake may be insignificant to a flexible surface system, but important to a pressure vessel, buried tunnel, landing pad, or long pipeline. Local geology controls foundation behavior. Cavities, ice-rich ground, fractured rock, and loose regolith respond differently to load and temperature. Choosing a site means listening to both the visible surface and the history beneath it. Cerberus also changes the emotional scale of the route. The red plain is not merely an archive under glass. It contracts, it fractures, meteoroids strike it, dust moves across fresh-looking lava. A habitat built here would stand on a planet with an active pulse, faint enough that a shielded seismometer was required to hear it, yet real enough to cross hundreds of kilometers of stone before reaching the instrument in Elysium. East of the main Elysium province, the route reaches Jezero crater. Perseverance landed there on February 18, 2021, after a descent that used a heat shield, parachute, powered descent stage, and cables to place the rover on its wheels. The sequence lasted minutes. Its complexity demonstrated how little help the atmosphere provides to a heavy arriving machine and how precisely engineering must replace that missing help. Jezero is an impact crater nested near the edge of a much larger impact structure, Isidis Planitia. The Isidis basin spans roughly 1,200 kilometers, while Jezero is a local feature within its western margin. This nesting matters. The first impact excavated and altered a broad region. A later impact opened Jezero. Rivers, lake water, sediment, lava, wind, and billions of years of exposure then modified the smaller crater. From orbit, Jezero offered a rare combination. A valley cuts through the rim. A fan-shaped deposit rests on the crater floor. Minerals associated with alteration by water occur in the region. Another channel leads away from the former basin. Together, the landforms show that water entered, stood within, and left a crater that is dry today. The rover was sent not to a present lake, but to a geological memory of one. The landing site also reveals why regional labels can mislead. Jezero is called a crater, yet its science includes volcanic rock, sediment, groundwater alteration, river transport, wind erosion, and impact history. Isidis is called a plain, yet it began as an enormous wound in the crust. Planetary names identify shapes on a map. They do not limit the number of processes preserved inside those shapes. For human exploration, Jezero is scientifically rich and operationally demanding. A delta contains slopes, ledges, loose material, and boulders. Dust and sand can block direct routes. Perseverance often travels around hazards that look small from orbit. A person could cross some ground faster than a rover, but a pressurized vehicle, suit, power system, communication link, and return margin would turn each excursion into a planned chain. Night in Jezero still returns to the atmospheric baseline. The crater floor lies lower than its rim, but not beneath an ocean of air. Temperature drops. Radiation continues. Dust remains on every exposed surface. The former lake does not refill. The landscape contains evidence that Mars once supported more persistent surface water, while the present environment explains why a human visitor must bring an artificial atmosphere to study it. Around 3.5 billion years ago, a river flowed into Lake Jezero and delivered mud, sand, and larger debris. As moving water entered the standing lake, it slowed. Sediment fell from the flow and built a delta. The basic geometry is familiar from Earth, but the structure on Mars has survived across a span of time longer than the entire visible history of complex life on our planet. Perseverance reached the delta after crossing the crater floor. Images revealed layered sedimentary rocks, including fine-grained units that mission scientists consider favorable for preserving possible signs of ancient microbial life. That wording is precise. A rock can record an environment that was habitable for microbes without containing evidence that organisms were present. The rover searches for potential biosignatures while keeping environment and life as separate claims. The water story grew more complex after landing. Crater floor rocks included igneous material rather than only sediment washed into the basin. Some of those rocks interacted with water. Delta observations also showed evidence of later high-energy floods capable of moving large boulders. Jezero was not one calm lake preserved in a single moment. It changed through volcanic, lake, river, flood, groundwater, and dry surface phases. This complexity is why sample context matters. A core taken from layered delta rock carries information about the precise place it came from, the layer around it, nearby structures, chemistry, and the sequence interpreted from surrounding terrain. A loose stone without that context can still be interesting, but it is harder to place in time. The rover is building a geological argument one abrasion patch, image, and sealed core at a time. The ancient lake also sharpens the present contrast. Mars once allowed rivers and standing water under conditions different from today's. The planet then lost much of its atmosphere and surface water as climate and interior processes evolved. Some water remains locked in ice, minerals, and the subsurface. At Jezero, the dry delta stands beneath air too thin for exposed liquid water to remain stable for long. A human looking across the delta from a protected rover would see a place chosen because water once gathered there. The visor would face dust, low pressure, and radiation. The life support system would recycle water inside the vehicle. Past and present would occupy the same view. One is written in stone. The other is maintained by pumps, tanks, filters, and seals. West of Jezero, the terrain rises toward Nili Planum and the broad, dark province of Syrtis Major. This is part of the transition from the northern lowlands into older cratered terrain. Orbital mapping shows a patchwork rather than a single boundary line. Impact structures, fractured plateaus, plains deposits, volcanic surfaces, channels, and eroded remnants meet across the region. Syrtis Major was one of the first surface markings on another planet recognized through early telescopes. It appears dark not because it is a sea, as some observers once imagined, but because winds expose dark volcanic material and move brighter dust. The boundary can change subtly as dust covers or uncovers the surface. Mars is red from a distance, yet regional color depends on the material visible at the topmost layer. The region near Jezero attracted mission planners, partly because ancient rocks remain exposed. Impacts can excavate material from depth. Erosion can open old layers. Water can alter minerals and leave chemical records. Lava can cover one surface while preserving another beneath it. A rover moving a few kilometers can therefore pass between rocks formed in different settings and separated by long intervals. Altitude rises unevenly through the transition. That small shift affects air density, entry calculations, local temperature, and the energy required to climb. It also changes what orbital radar and spectroscopy can infer about buried ice or exposed minerals. There is no sharp moment when a traveler leaves the north and enters the south. The planetary dichotomy is crossed through a zone, not through a doorway. For a settlement, the same variety is both resource and complication. Diverse rocks may supply useful elements. Exposed layers can support science. Slopes and broken ground increase mobility risk. Dust behavior changes with surface texture. Communications can be blocked by local relief. A site promising on one map may become less useful when the engineering maps are placed on top of the geological one. The survival answer remains unchanged because the transition rearranges terrain rather than atmosphere. Dark rock can warm in sunlight. A low pocket can hold slightly denser gas. Neither creates oxygen, neither restores a magnetic shield. Mars offers gradients, and careful exploration lives within those gradients, but every route still begins inside pressure and ends by returning to pressure before the stored margins run out. Far to the south lies Hellas Planitia, one of the deepest and largest visible impact basins on Mars. A colossal collision excavated the crust early in planetary history, leaving a broad depression surrounded by higher terrain. Later processes softened parts of the structure with sediment, frost, dust, and erosion. On a global elevation map, Hellas appears as a deep blue hollow inside the elevated southern hemisphere. Depth gives Hellas more atmosphere overhead than most Martian surfaces. Pressure on the basin floor can be substantially higher than at the highlands and volcanic summits. That makes Hellas useful in studies of weather, clouds, frost, and entry. It does not make the basin breathable. Even the thickest natural Martian surface air remains a mostly carbon dioxide environment, far below human pressure requirements. The basin also affects circulation. Air descends and rises along enormous slopes. Dust can gather within the depression and move around its rim. Frost and clouds respond to season and elevation. Small gullies and channels cut some scarps, while broad interior surfaces preserve deposits from multiple eras. Hellas is not merely a hole. It is a regional weather system placed inside an ancient impact structure. Temperature follows the same mixture of advantage and limit. Lower elevation can moderate some conditions, but southern latitude and seasonal darkness can bring severe cold. Surface composition changes how sunlight is absorbed. Dust changes the energy balance. A habitat might gain a little pressure outside and still require nearly the same pressure inside. Its greatest benefit could come during entry, not during an unprotected walk. Even that entry benefit has boundaries. A deeper atmosphere gives a vehicle more gas to push against. Yet Hellas also presents regional winds, dust, high surrounding terrain, and a long climb for any later ascent toward orbit. Site selection cannot maximize pressure alone. The complete mission must land, operate, communicate, obtain resources, and depart. One favorable number enters a larger equation whose other terms may point elsewhere. The basin illustrates a rule that will return at Olympus Mons in reverse. Mars changes dramatically with elevation, yet the entire accessible elevation range lies outside naked human habitability. Hellas is better than a summit in some engineering variables. It remains worse than the inside of a working airlock in all immediate biological ones. Planetary extremes can be compared with each other without confusing either extreme for Earth. Standing in imagination on the floor of Hellas, the encircling rim would be too distant to read as a crater wall in one glance. The structure is regional, not architectural. The impact happened in a moment, while the basin's later history unfolded across billions of years. One Martian night within it lasts only 24 hours and 39 minutes. For an unprotected person, that is still far too long. Outside Hellas, the southern highlands spread across much of the hemisphere as heavily cratered terrain. Each preserved crater is a minimum age marker. The surface beneath existed before the impact, and anything laid over the crater came later. Where craters overlap, relative sequence becomes visible. The younger rim cuts the older one. Ejecta from a fresh impact blanket structures already present. These highlands retain more of the early impact record than the resurfaced northern plains. They also preserve valley networks, carved when Mars supported a different water cycle. Some valleys branch through the landscape in patterns consistent with water moving downhill, across, or beneath the surface. Ancient basins contain deposits formed in lakes. Minerals altered by water remain after the rivers and lakes are gone. The word ancient does not mean unchanged. Wind continues to shift dust and sand. Frost acts at high latitudes and on shaded slopes. Meteoroids strike. Gravity moves loose material down crater walls. Thermal cycling cracks rock. Mars operates slowly at human scale, but a billion years gives even slow processes a long reach. The most ancient surfaces are palimpsests, rather than untouched museum floors. The highlands also carry strong patches of remanent crustal magnetism. Measurements from orbit show alternating magnetic structures in Old Southern Crust, evidence connected to an early global dynamo. Large impact basins lack some of that magnetic signature, helping scientists constrain when impacts and dynamo activity occurred. The rocks preserve a planetary field that no longer extends around the modern world. For explorers, old terrain can offer exposed scientific history at the price of rougher landing and travel. Crater rims create slopes. Ejecta creates blocks. Elevation reduces the already thin air. Communications depend on line of sight. A rover can spend an entire day navigating around one obstacle field that an orbital image compresses into texture. A human mission would choose its highland route with an exit margin measured in power, oxygen, and time. At night, the oldest landscape and the newest machine meet. The ground may record the first billion years of Mars. The habitat may have been operating for only months. One is durable but lifeless. The other is fragile but occupied. Survival depends on keeping the young structure sealed against an environment that has been thinning, cooling, and weathering the highlands for ages. Near the boundary between southern highlands and northern lowlands lies Gale crater, the home of curiosity since August 2012. Gale is about 154 kilometers across, large enough to contain a central mountain rising roughly 5 kilometers above the crater floor. The mission team calls that mountain Mount Sharp. Its formal Martian name is Ulivable Mons. Mount Sharp is not a volcanic cone. It is a mound of layered rock. From orbit and from the rover's cameras, bands climb the mountain like pages stacked through time. Lower layers include clay-bearing materials associated with water. Higher units record different conditions, including salt-bearing rocks and surfaces shaped under drier climates. Curiosity was sent to read that environmental transition by driving upward through the sequence. The rover first explored Yellowknife Bay near the crater floor, where mudstone and mineral veins supported the conclusion that an ancient lake environment could have been habitable for microbes. Habitable does not mean inhabited. It describes conditions that could supply liquid water, chemical ingredients, and usable energy. The distinction lets the rock speak at the level the evidence supports. As curiosity climbs, every meter upward can represent a shift in the ancient environment rather than one fixed interval of time. Layers can be missing. Wind can remove material. Water can alter rock after deposition. Sand dunes can cross the rover's route in the present. The mountain is a record assembled and edited by geological processes, not a perfectly bound chronology. Gale also supplied the first direct long-term radiation measurements on the Martian surface. The average of 0.67 millisieverts per day, measured during the sighted interval, belongs to this crater under its particular altitude, atmosphere, and solar conditions. The same site therefore holds evidence of past habitability and a measured warning about present human exposure. A traveler could look from the rover's route toward 5 kilometers of layered mountain and see two planets in one place. Ancient Gale held lakes. Modern Gale holds dust devils, cold nights, thin carbon dioxide air, and radiation. The mountain survives because it is rock. The rover survives because it carries heat, power, computation, and carefully managed mechanisms. A human would need those protections expanded into a complete living world. Curiosity's path through Gale turns a regional tour into a vertical one. The rover does not need to circle the planet to encounter different eras. It drives from one band of Mount Sharp into another. Cameras describe bedding and fractures. A drill gathers powdered rock. Instruments measure minerals, elements, gases, radiation, humidity, pressure, and temperature. Each dataset adds a coordinate to the history, what formed, under which conditions, and what changed afterward. The lower mountain preserves evidence of repeated lake-related environments rather than one permanent body of water. Mud settled. Minerals formed or changed in water. Later drying left salts. Wind removed softer layers and exposed harder ones. The sequence shows that Mars did not move from wet to dry in a single clean step. Conditions varied across location and time, with habitable intervals followed by less favorable ones. That finding alters the meaning of the modern crater. Gale is not selected because it is warm or protected now. It is selected because present erosion has opened old pages. The thin atmosphere that makes the surface hostile also allows wind to keep reshaping exposures. The environment damaging to a visitor can be useful to geology, slowly uncovering layers that a rover can reach. At the surface today, the air presses with only about 6 millibars near the Martian reference level, varying through Gale's weather and seasons. Curiosity measures that pressure rise and fall each sol. It also watches dust opacity, cloud movement, ground temperature, and ultraviolet exposure. Ancient climate is read from stone. Present climate is read directly from sensors standing on the stone. The two records must not be merged. A clay mineral says water altered a rock under past conditions. It does not say liquid water rests beside the rover now. An organic molecule can be part of chemistry without being evidence of an organism. A habitable ancient environment is not a confirmed habitat. The strength of Mars science comes from maintaining those boundaries while continuing to search. For future crews, Gale offers another form of boundary. A 5-kilometer mountain invites travel, but every kilometer away from shelter increases the amount of stored life support required to return. A rover carrying humans would need pressure integrity across rough ground, thermal control through shadow and sunlight, navigation around sand, and reserves for a path made longer by one blocked route. Mount Sharp therefore becomes both archive and clock. Its layers span enormous time, while a human excursion would be governed by hours. The scientist may want to continue upward. The engineer watches oxygen, battery state, suit condition, dust, radiation, and distance. On Mars, curiosity can choose the destination. Survival decides the turnaround point. West of Gale, the surface opens into the largest canyon system in the solar system. Valles Marineris extends about 3,870 to 4,000 kilometers from the fractured terrain of Noctis Labyrinthus toward chaotic ground and outflow channels in the east. At its widest, it spans about 600 kilometers. Its deepest sections descend roughly 9 to 10 kilometers below the surrounding plateau. Those numbers resist a single view. A person standing on one floor would not see the entire system as a canyon. The opposite wall might lie beyond the horizon. Separate troughs run beside one another, divided by ridges and plateaus. Landslide deposits spread across floors. Layered mounds rise inside some cosmata. Side canyons enter the main system, and eastern valleys break into terrain disrupted on a regional scale. Placed across the United States, the canyon's length would reach roughly from the Pacific coast toward the Atlantic. Its width at the broadest point would cover the distance between cities rather than neighborhoods. Yet even that comparison compresses the vertical scale. A 9-kilometer wall carries different lighting, pressure, temperature, and geology from top to bottom. The canyon is not one line on a map, but a stack of regional environments. The name Valles Marineris honors Mariner 9, the first spacecraft to orbit another planet. When it reached Mars in 1971, a global dust storm hid much of the surface. As the dust cleared, the orbiter mapped volcanoes, channels, and the canyon system in a new planetary context. Earlier telescopes had shown markings. Orbital imaging revealed topography vast enough to reorganize the map. Elevation gives the canyon an unusual environmental range. A high rim stands in thinner, colder air than a deep floor. Shadows can persist against steep walls. Slopes receive sunlight at changing angles. Dust and water ice clouds move through the regional circulation. More atmosphere at depth may help some operations, but canyon walls can block communication and complicate landing, navigation, and escape routes. The scale also changes emergency planning. On Earth, a road may climb out of a canyon within hours. In Valles Marineris, a route from floor to plateau crosses kilometers of relief through landslides, cliffs, fractures, and loose material. A pressurized vehicle descending into the system would need a reliable path back, or a second protected destination ahead. The canyon offers shelter from some radiation directions while creating isolation of another kind. Potential resources and science are equally large. Layered deposits record water, wind, volcanic material, and chemical alteration. Landslides expose material from the walls. Some hydrated minerals have been detected from orbit. The canyon is not a single environment, and any claim about it must be attached to a specific chasma, slope, layer, and season. Across one Martian night, darkness would reach different parts of the system at different times. One wall loses the sun while another remains lit. The floor cools beneath a narrow strip of sky. A habitat may gain shielding from rock, yet it still must keep pressure, oxygen, heat, and power. The canyon changes the shape of the danger. It does not remove the danger. Valles Marineris did not form as a larger version of Earth's Grand Canyon. Running water enlarged parts of the system and left important deposits, but the initial structure is tied to tectonic extension around Tharsis. As the enormous volcanic province rose to the west, stresses stretched the surrounding crust. Faults opened. Blocks dropped between them. Long troughs formed where the crust pulled apart. The process is visible in the canyon's geometry. Many sections follow roughly east-west structural trends. Parallel chasmata sit beside one another. Their walls expose repeated faulting and collapse rather than one continuous river-cut valley. Noctis Labyrinthus at the western end preserves a mesh of intersecting fractures, a broken transition between the Tharsis Plateau and the main canyon troughs. Once relief existed, gravity took over much of the enlargement. Walls kilometers high became unstable. Landslides released masses of rock that traveled across the floors and left lobe deposits. Collapse widened the troughs. Erosion worked on exposed layers. In the east, groundwater release and catastrophic flow may have helped create chaotic terrain and outflow channels leading toward the northern plains. NASA's mapped interpretation places the beginning of major faulting around 3.5 billion years ago, with the main growth largely ended by about 2 billion years ago. Those ages remain geological reconstructions rather than witnessed events. Crater counts, cross-cutting relationships, and the sequence of deposits provide the clock. Smaller slope failures can continue in the present. This history shows how regions connect. Tharsis rose. The nearby crust stretched. Valles Marineris opened. Material moved eastward. Water and sediment altered floors and channels. Dust later covered and uncovered surfaces. A geographic tour becomes a chain of causes, each province changing the conditions in the next. For a human base, fractured rock is both opportunity and warning. Cavities and overhangs may offer shielding. Exposed walls give access to layered geology. The same fractures can destabilize slopes. A buried habitat must be placed in material whose structure is understood. A protected volume beneath rock is useful only if the roof remains secure and the route to the surface remains open. At roughly 9.3 kilometers below the highest surrounding rim, in its deepest mapped section, the canyon seems capable of hiding an entire human world. It cannot hide that world from pressure loss inside its own walls. If a seal fails, the local atmosphere still waits outside at a small fraction of human requirements. Rock can supplement a habitat. It cannot replace the habitat. At the western head of Valles Marineris lies Noctis Labyrinthus, the labyrinth of night. The name fits a terrain of intersecting valleys, graben, mesas, and collapsed blocks. Instead of one canyon with two opposing walls, the surface breaks into a network. Flat-topped remnants stand between troughs. Shadows divide the ground into corridors whose geometry changes with every turn. Noctis occupies the transition into the Tharsis rise. Faults formed as the crust was stretched and elevated. Some troughs exposed layered deposits along their walls and floors. Landslides and wind later reshaped the openings. The result is a place where tectonic architecture remains visible at the surface, a map of extension drawn in negative space. From orbit, the maze can look navigable. At rover height, a shallow line on the map may become a scarp. A wide floor may contain blocks, dunes, or dust-covered fractures. A direct route may end at a wall, forcing a long reversal. Autonomous navigation reduces some delay, but every detour consumes energy and time. A crewed traverse would plan not only a destination, but alternate protected paths. The terrain offers natural shielding possibilities because steep walls block part of the sky. A carefully characterized alcove or subsurface void could reduce radiation from some directions and lessen temperature swings. It could also lose direct sunlight and line-of-sight communication. The same rock that protects a habitat can complicate power, radio links, access, and structural inspection. Night makes the name literal without changing the clock. The Martian soul remains 24.6 hours. Deep troughs enter shadow before the plateau. Radiative cooling begins while sunlit high ground still produces solar power. Batteries or cables must bridge that mismatch. A base designed around the light at one location must account for the horizon created by its own shelter. Noctis also demonstrates the limits of labels in another way. Night is not one condition. A shaded floor, a sunlit rim, and a pressurized interior can exist at once, each with a different temperature and energy balance. The outside air remains thin in all three. A person crosses between them only through the controlled boundary of a suit or vehicle. The labyrinth is therefore not merely an obstacle. It is a design problem written at landscape scale. Roots, shadows, slopes, shielding, communication, and geology interact. A safe night here could be easier in one variable and harder in four others. Mars rarely gives a benefit without changing the balance around it. Beyond Noctis, the ground rises into Tharsis, an immense volcanic and tectonic province. It is not one mountain. It is a broad bulge in the Martian crust, thousands of kilometers across, carrying Olympus Mons, the aligned Tharsis mantas, Alba Mons, lava plains, fractures, and collapsed calderas. On a global topographic map, Tharsis changes the shape of the planet. The province accumulated through repeated volcanic activity over a long span of Martian history. Lava spread across older terrain. Magma intruded below the surface. The added mass loaded the lithosphere, while uplift and internal pressure created systems of faults radiating away from the rise. Valles Marineris is the most visible connected response, but fractures extend across a far wider region. Earth's crust is divided into moving plates, and hotspot can build a chain as a plate passes overhead. Mars lacks that style of global plate motion. A volcanic source can therefore keep adding material to broadly the same region. Lower Martian gravity also allows mountains to grow taller before their own weight drives the same kinds of collapse expected on Earth. Tharsis changed more than topography. A mass this large influenced slopes across portions of the planet, redirected drainage, and affected stress patterns in the crust. Volcanic gases may have contributed to the atmosphere at different times. The province is both a place and an event distributed through time, one of the major reorganizations of the Martian surface. For landing, elevation is a penalty. High ground sits beneath less atmosphere, leaving less gas for a heat shield and parachute to use. Engines must do more work. For surface life, pressure falls below the already low reference. Temperature can be severe. A summit may receive broad sunlight and communication views while demanding greater ascent, shielding, and thermal margins. The exposed volcanic materials could provide useful construction and scientific targets. Lava tubes, if confirmed safe and accessible at a chosen location, could offer shielding. Basaltic material can become aggregate or feedstock, but a theoretical resource does not become operational until its location, purity, excavation energy, processing method, and transport route are known. Tharsis feels powerful because one region has placed a load across a planet. It also feels still because no eruption has been witnessed there by modern spacecraft. Those impressions can coexist. The province records long-lived volcanism and enormous crustal change. A present human night on its surface would still be governed by the quiet operation of heaters, pressure regulators, filters, and shielding. At the western edge of Tharsis rises Olympus Mons, the largest known volcano in the solar system. NASA mapping describes a base more than 600 kilometers across and a height of about 26 to 27 kilometers relative to the surrounding plane or reference used. Its area is comparable to Arizona. The summit contains several overlapping calderas formed when magma withdrew and the roof above a reservoir collapsed. Olympus is a shield volcano. Its flanks were built by many fluid lava flows, spreading outward at shallow angles. The mountain is so broad that a person on the lower slope might not perceive a peak. The horizon would rise gradually. Curvature and distance hide the whole structure, just as they hide the full width of Valles Marineris. A steep scarp surrounds much of the base, reaching several kilometers high in places. Beyond it lies an aureole of ridged deposits extending across the plains. The exact history of the scarp and aureole involves gravity, lava, and deformation over long periods. Even the largest smooth shield has edges where the scale becomes abrupt. At the summit, atmospheric pressure is far below the 6 millibar reference. The high elevation reduces aerodynamic support for any aircraft or landing system and increases exposure to radiation compared with a deeper site. The broad caldera floor may look level, but reaching it is an ascent into a more complete approximation of vacuum. The volcano's size can also distort human comparisons. Everest rises 8,848 meters above Earth's sea level, while Olympus extends roughly 3 times that vertical measure from its reference. But Olympus formed under different gravity, crustal behavior, erosion, and datum. The point is not that one mountain wins. The point is that planetary conditions produce different allowable forms. An expedition to the summit would require a chain of protected mobility. A pressurized vehicle climbs for hundreds of kilometers. Power and thermal systems cross long slopes. Communication is maintained beyond local horizons. Spare parts and retreat options travel with the crew. A suit excursion outside the vehicle remains limited, even when the view extends across a province. Sunset from Olympus Mons would arrive under an exceptionally thin sky. The sun would still take nearly the same 24.6-hour rhythm to return, but the night would open above a summit with almost no atmospheric buffer. The volcano supplies height, history, and a planetary view. It supplies none of the air required to remain there unprotected until dawn. Southeast of Olympus Mons, 3 more giant shield volcanoes cross Tharsis in a northeast to southwest line: Cerberus Mons, Pavonis Mons, and Arsha Mons. NASA's regional mapping places each at roughly 350 to 400 kilometers in diameter and about 17 kilometers above the surrounding plain. They are separated by hundreds of kilometers, yet their alignment makes them read as one structure on a global map. Ascraeus stands in the north, Pavonis near the Martian equator, and Arsha in the south. Each has a summit caldera and flanks built by overlapping lava flows. The line follows a buried fracture trend within the Tharsis rise. Magma repeatedly reached the surface along a zone of weakness, adding 3 enormous edifices to a province already loaded by volcanism. Their slopes preserve lava channels, tubes, collapse pits, and younger deposits laid over older ones. Some dark openings seen from orbit may connect to subsurface voids, though a useful human shelter would require direct mapping, structural tests, access planning, and environmental monitoring. A black spot in an orbital image is a scientific target, not a certified habitat. Arsha Mons also interacts with the atmosphere. Water ice clouds can form near the volcano as air rises and cools, sometimes stretching westward in a long plume during particular seasons and times of day. The feature is a cloud, not volcanic smoke. Mars can create weather around a volcano whose most recent eruptions occurred long before any human observer existed. Pavonis Mons occupies a location close to the equator, appealing in broad discussions of access and sunlight. Equatorial sites avoid the longest polar darkness and can offer regular day-night cycles. The altitude remains a major cost. A vehicle must climb through low pressure, and any aircraft must work with less density than it would on the plains below. The 3 volcanoes therefore become a controlled comparison. Similar broad form, different latitude, different local age relationships, different clouds, slopes, and access routes. Region by region study does not stop at the name Tharsis. It continues down to individual flanks and units because that is where engineering and geology become specific. Spacing adds another scale. NASA mapping places the 3 Tharsis Montes roughly 700 kilometers apart. A line connecting them looks compact on the globe, while surface travel between 2 would exceed many national road journeys on Earth. A base beside one volcano would not place the other 2 within easy reach. Planetary maps encourage the eye to treat provinces as neighborhoods. Operations restore the real distance. A night between the volcanoes would be framed by silhouettes too distant to feel like neighboring mountains. The internal habitat clock would track the same soul. Outside, pressure would sit below the global reference. Temperatures would fall, and the stars would show through a dusty atmosphere. Alignment on a map offers no shared shield. Each base would still have to make its own small Earth. Northwest of Tharsis lies Elysium Planitia, one of the smoother lowland regions on Mars. Low crater densities on many surfaces show that parts of the plain are geologically young compared with the ancient highlands. Lava and wind-blown deposits covered older terrain, erasing or burying much of its visible impact record. Smoothness here is evidence of resurfacing, not absence of history. Young is always relative on a planetary map. A surface can be hundreds of millions of years old and still belong to the younger chapters of Mars. Crater counting provides model ages by comparing the number and size of impacts across units. The method does not place a calendar beside every rock. It builds a statistical chronology, checked against which deposits cut or cover others. Broad lava plains can look operationally inviting. Slopes are gentle, and long sight lines help navigation and communication. Yet lava surfaces carry their own hazards. Flow margins create ridges. Collapsed pits open abruptly. Dust can hide rocks or cracks. A landing ellipse that appears smooth at one resolution needs closer images before a spacecraft commits to it. Amazonas also lies downwind of major volcanic and dust-producing regions under changing seasons. Bright dust mantles some areas while darker material appears elsewhere. Wind streaks reveal transport. The surface visible today may be a temporary coating over very different rock, which matters when choosing a drill site, foundation, or resource processing method. For solar power, a flat horizon is helpful. Morning light reaches panels without a canyon wall in the way, and evening light remains available later. A dust storm can remove that advantage without changing the horizon at all. Energy planning therefore combines topography with atmospheric probability, cleaning capacity, storage, and a backup able to hold life support through poor generation. The plain carries another useful lesson about apparent emptiness. A quiet field can contain buried flows, impact structures, ice-rich material, and a long climate record. Mars hides complexity under dust because dust is the last event recorded across much of the surface. A human base would begin by looking beneath that last event. When darkness crosses Amazonas, the plain loses heat toward a wide sky. No mountain blocks the view, but no mountain blocks incoming radiation either. Smooth terrain helps wheels. It does not help lungs. The regional advantages are real, narrow, and valuable precisely because the larger environmental problem remains so demanding. East of Valles Marineris, enormous outflow channels descend toward Chryse Planitia and the broader northern lowlands. Chaotic terrains at their heads contain broken blocks and collapsed ground. Downstream, streamlined islands, scoured surfaces, and broad channels record flows far larger than ordinary rivers. The leading interpretations involve catastrophic releases of water from underground or temporary reservoirs in ancient Mars. Viking 1 landed in Chryse Planitia in 1976. The site showed a rocky plain beneath a dusty sky, far from the dramatic channels visible at orbital scale. That difference mirrors Utopia. A regional name can contain landforms a surface camera never sees from one point. The rover or lander occupies meters. The geologic unit extends hundreds of kilometers. Farther north, Acidalia Planitia forms a darker section of the lowlands. Sediment from highland valleys and outflow systems may have entered parts of the northern basin over long periods. Wind then reworked the upper surface. Polygonal ground, impact craters, dust, and possible ice-related features add younger patterns. The lowland is a destination for material carried from elsewhere. This movement connects the map. Water and debris left fractured highlands, crossed channels, and entered lower basins. Lava arrived from volcanic sources. Dust traveled through the atmosphere. Impact ejecta spread outward. A region is not isolated simply because cartographers draw a boundary around its name. Mars is a system of sources, paths, and sinks. The lower elevation again offers a modest atmospheric benefit. At the surface, the air presses with only about 6 millibars near the reference datum, with deeper lowland locations carrying somewhat more. That can matter during entry and in precise engineering calculations. It does not change the requirement for a pressure vessel or turn carbon dioxide into oxygen. Chryse's history of flowing water might suggest local resources, but ancient flood evidence does not guarantee accessible modern ice at a chosen point. Resource prospecting requires radar, neutron measurements, thermal data, drilling, and direct sample analysis. A mission cannot fill a tank with a channel on a map. It needs a deposit with known depth, concentration, chemistry, and extraction cost. The old flood paths end in a modern lowland where no river continues to run. Night settles over streamlined islands and dusty stones. A protected base could use the low terrain and study the channels. Outside, the atmosphere still carries too little heat and pressure to preserve the world those channels remember. The route now turns to the North Pole, where bright ice and dark troughs form a spiral pattern around Planemborium. The permanent cap contains water ice layered with dust, while a seasonal coating of carbon dioxide frost grows during winter and retreats when sunlight returns. Radar, imaging, and spectroscopy reveal a climate archive stacked through repeated changes. The layers form because ice and dust accumulate at different rates as Mars's orbit and axial tilt vary over long cycles. Wind removes material from some slopes and deposits it elsewhere. Troughs cut through the stack, exposing bands that can be followed around the cap. Like Mount Sharp, the pole stores time vertically, but the material is dominated by ice and dust rather than lithified lake sediment. Season changes the visible boundary. During northern winter, carbon dioxide from the atmosphere freezes onto the ground, expanding the bright cap and reducing global atmospheric mass. In spring, the frost sublimes directly back into the gas. Pressure rises elsewhere. The atmosphere and the surface exchange a major constituent in an annual cycle. Water ice makes the polar region important to the inventory of Martian resources and climate history. It also creates difficult conditions for human systems. Temperatures fall severely. Seasonal darkness can interrupt solar generation. Ice-rich ground expands, contracts, and can affect foundations. Extracting water requires energy, clean handling, and separation from dust and salts. The pole provides shielding material in abundance, but building within ice introduces structural and thermal questions. Waste heat can change the material around a habitat. Sublimation can create voids. Layers may slide along slopes. A design useful in dry equatorial rock may not transfer to a polar ice deposit. Resources and foundations are the same material, so using one changes the other. Communication and navigation also meet geometry at high latitude. The sun follows low seasonal paths. Earth may sit near the horizon from a surface antenna. Orbiters provide relays, but their passes must be scheduled and redundant. A storm or hardware faults during polar night occurs when local solar recovery is weakest. The North Cap looks like a reservoir, a record, and a landscape at once. It can answer questions about past climate and perhaps supply future explorers. It cannot be treated as a frozen lake ready for use. Every kilogram of water would be located, excavated, melted, purified, stored, and protected inside a system that continues working while the outside temperature falls. The South Pole follows a different seasonal expression. A permanent cap includes water ice and a residual deposit of carbon dioxide ice, while winter lays down a broader seasonal layer of frozen carbon dioxide. In some areas, that seasonal slab becomes translucent. Sunlight passes through and warms the dark ground beneath before the overlying ice has disappeared. Carbon dioxide at the base changes directly from solid to gas. Trapped beneath the slab, the gas pressure rises until it finds or creates an opening. A jet carries dust and sand upward. The material falls in dark fans across the bright ice, often tracing wind direction. Repeated flow below the slab erodes branching channels called arenaform terrain because their planform resembles spiders. NASA observations describe seasonal ice around a meter thick in the studied settings, with individual dark spots tens of meters across and fans extending much farther. The exact dimensions vary by location. The important mechanism is phase change under a translucent slab, a process made possible by the thin carbon dioxide atmosphere and the seasonal energy cycle. No organism makes the spiders. No liquid river is required. Gas does the carving. The landforms are a useful warning against interpreting an unfamiliar planet through one earthly resemblance. Branches can come from roots, streams, fractures, or flowing gas. The shape begins the investigation. Composition, timing, temperature, and motion identify the process. For explorers, seasonal jets introduce a local hazard. A surface that looks continuous can hold pressurized gas below it. Dust can erupt and fall across equipment. A landing pad, cable route, or foundation placed on seasonal slab terrain would face changes as ice appears and vanishes. Polar mapping must include time of year, not only coordinates. The South Cap also stores enough frozen carbon dioxide that releasing all of it would change global pressure. But NASA's assessment shows that accessible Martian carbon dioxide is far too limited to create an Earth-like atmosphere. Even doubling a pressure below 1% of Earth's remains, far below what an unprotected human requires. Terraforming language can make a factor of 2 sound larger than the starting point allows. During southern winter, darkness and cold deepen while atmospheric gas becomes ground ice. In spring, the surface seems to breathe as carbon dioxide returns to the air through frost retreat and jets. It is a planetary respiration made of phase change, not biology. A human inside a polar habitat would listen to pumps performing the biological work the outside cycle does not. The poles lead back to dust because Mars's seasons couple frost, pressure, wind, water vapor, and suspended particles across the globe. Local storms can rise along cap edges or over warm surfaces. Regional storms spread across large provinces. In some years, dust expands until much of the planet is obscured. The term global describes extent, not a wall of dense air. Dust absorbs sunlight and infrared energy. As the atmosphere warms, circulation changes and can lift more dust. The surface below receives less direct light and may cool, while the middle atmosphere becomes warmer. Water vapor can be carried to higher altitudes where it is more vulnerable to loss. A storm is therefore both weather and a participant in long-term climate processes. The 2018 global storm ended the Opportunity rover's mission after more than 14 years of operation. Reduced sunlight limited the power available to its solar arrays. Curiosity, using a radioisotope power source, continued working and measured the changing dust inside Gale crater. Two machines under the same sky experienced the event differently because their energy systems were different. A human habitat cannot treat reduced sunlight as a pause. Fans circulate air. Carbon dioxide scrubbers work. Heaters protect equipment and water. Computers, communications, medical devices, and food systems continue drawing power. Stored energy must cover the interval, and the design must allow for dust on panels after the sky begins to clear. Wind can also move dust into seals and radiators while depositing uneven thermal blankets on surfaces. Cleaning requires energy and may expose people or robots to more wear. A device designed to clean another device becomes part of the maintenance chain. The storm does not need to knock the habitat over. It only needs to reduce margins across several systems at once. Forecasting becomes a form of resource management. Orbiters observe storm growth beyond the horizon. Surface instruments track pressure, temperature, wind, and opacity. Models estimate where dust may travel and how strongly sunlight may fall. A crew can postpone an excursion, charge storage early, or protect exposed equipment. Prediction does not remove the storm. It converts some uncertainty into time, and time is one of the most useful reserves a closed system can hold. Seasonal carbon dioxide exchange changes surface pressure by up to roughly 30%, while dust changes temperature and circulation. That combination means the external environment is not a fixed test chamber. Hardware experiences cycles. Joints, membranes, lubricants, and coatings age under repeated pressure, temperature, ultraviolet, and abrasive exposure. When a global storm enters the night side, it does not stop. Dust remains aloft above a surface without sunlight. The interior habitat keeps its own weather, power, and clock. This is the recurring Mars principle at its broadest scale. The planet runs a climate, but human survival requires a second climate enclosed within it. After the storm, light returns through an atmosphere still carrying ordinary background dust. To human eyes, the daytime Martian sky would usually appear tan, salmon, or pinkish, rather than the deep blue familiar on Earth. Fine particles scatter and absorb sunlight differently from the molecules and aerosols in our atmosphere. Color also changes with camera calibration, dust loading, sun angle, and the purpose of an image product. Near sunrise or sunset, the region around the sun can take on a bluish glow. Viking 2 recorded this effect at Utopia Planitia, and later rovers returned clearer examples. Dust particles allow blue light traveling close to the sun's direction to reach the observer more effectively, while the wider sky remains warm-toned. Earth often gives blue days and red sunsets. Mars can offer the visual reversal. The sun itself appears smaller because Mars orbits farther away. At an average distance of 228 million kilometers from the sun, the planet receives less solar energy than Earth. The disk still provides a clear daily clock. It rises, crosses a dusty sky, and sets about 24 hours and 39 minutes after the previous sunrise. Familiar motion occurs inside an unfamiliar optical system. A sunset photograph can therefore be accurate and still fail to represent what a person would see. Rover cameras use filters and processing to serve science. Some products are white balanced to show rock colors as if illuminated on Earth. Others approximate natural Martian color. Raw detector values are not a finished human view, and a finished view must state how it was made. Inside a habitat, windows create another set of choices. Multiple pressure panes, radiation protection, dust coatings, and ultraviolet filters alter transmission. A perfectly clear wall would offer a broad view, but create thermal and radiation challenges. A small protected window reduces exposure, but narrows the sky. External cameras can provide color-corrected views without weakening the pressure shell. The blue glow also shows how a thin atmosphere can be visually present while biologically useless. Only a small quantity of dust and gas is needed to color a long path of sunlight near the horizon. The eye reads sky and assumes air. the lungs meet carbon dioxide at a pressure below 1% of Earth's. Beauty and breathability are independent variables. As darkness deepens, the dust-muted horizon gives way to stars. Phobos may cross quickly. Deimos may move more slowly above the surface. The scene feels like night because light has changed. For the habitat, night is defined less poetically. Solar input falls, radiators and heaters enter a different balance, batteries carry load, and every seal continues holding back the colored air outside. Mars has two small moons, Phobos and Deimos. Both are dark, irregular, and far smaller than Earth's moon. They are named for companions of the Greek war god Ares, whose Roman counterpart is Mars. From the surface, they would not create the broad, bright disk familiar on Earth. Their motions and apparent sizes are different, and Phobos in particular moves through the sky with unusual speed. Phobos orbits close to Mars, so close that it circles the planet faster than Mars rotates. To a surface observer in many latitudes, it rises in the west and moves eastward, crossing the sky in only a few hours. Its disk can pass in front of the sun, producing a brief transit rather than the long total eclipse possible with Earth's larger moon. Tidal interactions are drawing Phobos gradually inward. NASA summaries project that in roughly 40 to 50 million years, it may strike Mars or break apart, perhaps creating a temporary ring. That future is distant in human terms and short beside the age of the solar system. The moon carries a visible clock nested inside the slower evolution of an orbit. Deimos is smaller and farther away. It moves across the sky more slowly and appears star-like or planet-like rather than large and moon-like. Its loose surface material softens some crater shapes. Together, the moons remind us that familiar categories can contain very different objects. A moon can be a world-sized sphere, or it can be a dark body only a few tens of kilometers across. For navigation and science, their positions are predictable. Cameras have used transits to refine orbital knowledge. The moons may also preserve information about the early Mars system, though their origin remains debated. They could be captured asteroid-like bodies, products of impacts, or bodies altered after formation. Shape alone does not settle the history. A human crew would see Phobos cross during part of a working evening and still measure the night by habitat schedules. External operations end according to suit consumables, radiation forecasts, terrain, and power, not by moonlight. Deimos provides little useful illumination. Phobos moves quickly. Neither moon warms the surface or changes the composition of the air. The nearly Earth-length soul gives the scene its strongest familiarity. A person could eat an evening meal, finish maintenance, speak with crewmates, and watch darkness through a camera. Outside, the same 24 6-hour cycle drives temperature and power. Mars offers a recognizable night overhead. Survival depends on never mistaking recognition for protection. A safe Martian night begins with a sealed volume. The walls hold an internal atmosphere against an exterior pressure commonly measured in single-digit millibars. At the surface, the air presses with only about 6 millibars near the datum. Every square meter of habitat wall therefore carries a substantial outward load from the gas inside. Shape, material, joints, windows, doors, and penetrations all become parts of the pressure system. The atmosphere inside must also be managed, not merely stored. Oxygen is consumed. Carbon dioxide and water vapor are produced. Trace contaminants come from materials, cooking, experiments, cleaning, and people. Fans prevent pockets from forming. Sensors provide redundancy. Filters and scrubbers are replaced or regenerated. A quiet room is supported by continuous molecular work. Temperature control links directly to that circulation. Heat comes from occupants, electronics, lights, batteries, and chemical processes. Heat leaves through walls, radiators, airlocks, and the ground. The balance changes from day to night and from dust storm to clear sky. A habitat cannot depend on one thermostat connected to one heater. It needs zones, loops, bypasses, alarms, and methods to survive a failed component. Water forms another closed chain. People drink, prepare food, wash, and produce moisture and waste. Recovery systems reclaim as much as practical, while stored reserves cover losses and maintenance. Local ice could reduce the mass launched from Earth, but extraction equipment, purification, storage, and testing must work before the resource becomes part of life support. Ice outside is potential. Clean water inside is inventory. Radiation changes where people spend the night. Sleeping quarters can occupy the most shielded part of the habitat, surrounded by water tanks, food, equipment, or Martian material. A smaller storm shelter provides greater protection during a solar particle event. Dosimeters track exposure by location and task. Shielding is designed around mission duration, not one evening. Dust determines how the room connects to the surface. A simple door would vent the atmosphere. An airlock transfers people while conserving as much gas as possible. Suit ports may keep contaminated suit exteriors outside. Tools and samples follow separate cleaning paths. Pressure checks occur before either hatch opens. The sequence becomes ritual because one skipped step can place the entire interior at risk. Power holds all of these loops together. Solar arrays, batteries, radioisotope systems, fission power, or some combination must provide continuous energy with serviceable distribution. Critical loads have priority. One failed cable cannot darken every fan. One dust storm cannot end oxygen processing. The habitat is not a house placed on Mars. It is an environmental machine whose occupied room happens to feel like a house. Perseverance carried a small experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. It drew in Martian atmosphere, compressed and heated it, and electrochemically split carbon dioxide molecules to produce oxygen. The device proved a principle using material already present on Mars. It did not turn the air around the rover into a breathable zone. MOXIE operated 16 times and produced a total of about 122 grams of oxygen. Its peak production reached roughly 12 grams per hour. NASA compared the total with about 4 hours of breathing for one astronaut. A future system intended for a crew or for rocket oxidizer would need to operate at a much larger scale for longer periods with storage, purification, maintenance, and reliable power. The distinction between demonstration and infrastructure matters. A machine can succeed 16 times without proving unattended operation for years. A larger plant changes heat rejection, dust filtration, compressors, seals, spare parts, and energy demand. Oxygen for breathing needs different handling from oxygen produced for propulsion, though both could come from the same atmospheric carbon dioxide resource. Local water follows the same progression. Orbital and surface missions show abundant ice in polar and subsurface reservoirs, but a base needs a mapped deposit close enough to reach. Drilling through ice-cemented ground consumes energy and wears equipment. Melted material carries dust and salts. Purification leaves waste streams that must be stored or processed. The resource becomes useful through a complete industrial chain. Construction material may also come from basaltic regolith. It could be compacted, sintered, cast into shielding blocks, or used as feedstock after processing. Each verb hides machinery. Excavators move soil. Screens separate grain sizes. Furnaces or binders consume energy and supplies. Quality control confirms that a pressure protecting or radiation shielding element actually meets its specification. The value of local resources is not that they make Mars naturally habitable. It is that they reduce what must cross interplanetary space. Carbon dioxide can become oxygen. Ice can become water, oxygen, and hydrogen. Rock can become shielding. The environment remains hostile while becoming partly usable. A desert can supply ingredients without supplying a meal. By the time a crew spends one ordinary night on Mars, months or years of machines may have prepared for it. Power has been generated, oxygen has been stored, water has been purified, shielding has been placed, spare filters wait in labeled compartments. The night's quiet would be the final product of engineering performed long before sunset. We have talked about a sol lasting 24 hours and 39 minutes, close enough to an earthly day that sunset and dawn keep a familiar rhythm. We have talked about a year lasting 687 Earth days, with long unequal seasons moving frost, pressure, water vapor, and dust from one part of the globe to another. We have talked about an atmosphere made mostly of carbon dioxide, pressing against the ground with only a few millibars and carrying almost none of the oxygen a person needs. We have talked about temperature falling through the night because thin air and a dry surface store little daytime heat. We have talked about radiation reaching the ground through an atmosphere less than 1% of Earth's, above a planet with no modern global magnetic shield. We have talked about Curiosity's measured average of 0.67 millisieverts per day during one interval at Gale, and the much longer exposure accumulated across a human mission. We have talked about dust small enough to color the sky and persistent enough to enter seals, filters, joints, radiators, and power plants. We have talked about perchlorate salts that turn local material into a processing problem before it becomes water, food system input, or a clean breathing space resource. We have crossed Utopia's low plane, Elysium seismometer, and Cerberus Fossae's young fractures. We have entered Jezero's dry delta and climbed Gale's layered mountain. We have moved from the northern lowlands into the old cratered south, where rocks preserve the memory of water and a magnetic field no longer present around the planet. We have followed Valles Marineris for nearly 4,000 kilometers, watched faults open beside Tharsis, and climbed in scale to Olympus Mons. We have crossed the aligned volcanoes, the young-looking surface of Amazones, and the outflow paths toward Chryse and Acidalia. Elevation changed, terrain changed, the need for a pressure wall did not. We have reached polar layers made of ice and dust, seen carbon dioxide freeze from the atmosphere, and followed gas beneath translucent slabs until it carved spiders and carried dark fans across the spring surface. We have watched storms join local dust to the circulation of an entire world. And we have returned to the small illuminated room where all those regional facts become engineering: pressure, oxygen, heat, water, shielding, filtration, power, repair. None can be assumed because the planet supplies none in the complete form a human body requires. A safe night is not found on the map. It is constructed at one point on the map. The direct answer to the title is that no unprotected human could survive a single Martian night because the body would lose usable oxygen and pressure long before dawn. The cold would deepen across the hours. Radiation would add to the mission's cumulative exposure. Dust would complicate equipment and recovery. These hazards overlap, but the first boundary is the air itself. No region changes that answer. Hellas provides more atmospheric pressure than Olympus Mons, but still far too little. An equatorial noon can warm the ground above freezing, but the warmth is local and temporary. A canyon wall can block some of the sky, but it does not make oxygen. Polar ice can supply future water, but it does not become a drink without excavation and treatment. The word unprotected carries the entire distinction. Humans have already kept machines alive through thousands of Martian nights. Viking 1 operated for years. Curiosity and Perseverance use heaters, insulation, power, software, and protected electronics. Insight listened through winter until dust and declining power ended its mission. Engineering can function on Mars when it is designed around the actual environment. A human system is more demanding because a person cannot be powered down through cold weather or left without circulation. The habitat must maintain chemistry, pressure, temperature, and sanitation every minute. It must permit maintenance without exposing the crew to the environment being held outside. It must survive faults while people are still inside to repair them. The night is therefore possible under specific conditions. A pressurized habitat remains intact. Oxygen generation and carbon dioxide removal continue. Thermal control holds. Power reserves cover darkness and dust. Water remains liquid inside the system. Radiation shielding reduces exposure. Airlocks and suits keep dust from crossing into living space. A second path exists when the first component fails. That answer does not reduce Mars to hostility. The planet is not trying to harm anyone. 6 millibars is not an attack. Carbon dioxide is not malice. A cold surface beneath an open sky is simply the outcome of Mars's mass, distance, atmosphere, interior, and history. Danger describes the mismatch between environment and organism. Change the organism's surrounding system, and the outcome changes. The person remains biologically terrestrial, but the room travels with them as a portable environment. In that sense, human survival on Mars is not a conquest of the planet. It is an agreement with physics, maintained through measurements, materials, energy, and care. Imagine the first Martian evening that eventually feels ordinary. The crew has finished an excursion across a plain selected for accessible ice, safe landing, and useful geology. Suits remain connected outside the main pressure volume. Samples pass through a separate enclosure. Filters record another small rise in captured dust. Nothing in the procedure is improvised. Inside, the day resembles a day because the habitat is designed to make it so. Lights follow the 24 6-hour sol. Warm air moves through ducts. Water circles from use to recovery and back toward use. A meal contains ingredients brought from Earth and perhaps a few grown under controlled light. The familiar scene is assembled from closed loops. Beyond the wall, temperature falls across the regolith. Solar generation ends. Batteries and other sources take the load. A pressure sensor watches for a change too small for human ears. A radiation monitor adds another line to the mission record. The room remains quiet because the instruments are not. When you open an ordinary door on Earth, the room and the world exchange air freely. Pressure equalizes without ceremony. Rain has already been purified by a planetary water cycle. Soil supports food through ecosystems built over immense time. A magnetic field and thick atmosphere work without appearing on any household control panel. Mars moves those background services into the foreground. Opening a door becomes a pressure operation. Water becomes a measured loop. Air becomes inventory and chemistry. Soil becomes feedstock requiring analysis. Weather becomes an energy forecast. The habits of daily life reveal the planetary infrastructure hidden beneath daily life on Earth. This is the deeper reason to travel region by region. The map shows more than destinations. Utopia explains landing and ice. Jezero explains ancient water. Gale explains environmental change. Valles Marineris explains crustal stress. Tharsis explains volcanic scale. The poles explain a breathing atmosphere of carbon dioxide frost. Every region becomes one part of the habitat design conversation. The cruise calendar would slowly acquire regional memories. A filter changed after the Acidalia traverse, a drill bit worn against volcanic rock from Elysium, a radiation shelter exercised during a storm forecast over Amazonas, a vial of Jezero sediment stored behind shielding. Geography would enter daily language through maintenance rather than spectacle. The names printed on orbital maps would become names for routes, weather patterns, work orders, and shared experience. The habits would grow slowly, then become the culture of the outpost. This is how an alien planet would begin to feel inhabited. Not when its environment became easy, but when people learned its differences well enough to build dependable habits around them. The first ordinary Martian evening would therefore be extraordinary, only when viewed from a distance. To the people living it, success might sound like fans, pumps, a checklist, and a conversation about tomorrow's route. The greatest achievement would be repetition. One protected night, then another, then enough nights for a temporary outpost to acquire a history of its own. Return now to the globe. The northern plains curve away under a dusty twilight. Jezero's delta becomes a small fan inside a small crater inside the rim of Isidis. Gale's mountain becomes one layered point near the dichotomy. Valles Marineris narrows into a dark line. Tharsis lifts 4 immense volcanoes into the last sunlight. Farther south, Hellas gathers deeper air without gathering enough. The Old Highlands carry craters through shadow. At the North Pole, water, ice, and dust hold a layered climate record. At the south, carbon dioxide frost waits for spring sunlight to release gas beneath the slab. Phobos crosses above regions too large to see together from the ground. The whole planet rotates once every 24 hours and 39 minutes. That is close to home. Close enough for evening. Close enough for midnight. Close enough for morning. But similarity in time does not create similarity in environment. Mars keeps an almost familiar clock inside a world built from different limits. At the surface, the air presses with only about 6 millibars. The sentence was true at the beginning of the journey. It remains true after every region. More in a basin, less on a summit, never enough to breathe, never enough to hold the body safely through the dark. The answer is not that a human night on Mars can never happen. It is that the night must occur inside a human-made boundary. The habitat carries pressure where the planet has little, oxygen where the planet has almost none, warmth where the surface loses it, water where liquid cannot remain exposed, shielding beneath an open sky. Every safe room on Mars would be a small statement about Earth. Air is material. Water is inheritance. Heat is balance. Soil is chemistry. A living environment is not empty space around a person. It is a network of conditions held together over time. Outside, Mars continues without that network. Dust moves, frost forms, rock contracts, a moon crosses. The planet does not become more earthly because someone has arrived. The visitors become more attentive because Mars makes every supporting system visible. 6 millibars, carbon dioxide, cold stone, ancient water, a sealed light in the distance. One planet, many regions, one protected room. Morning remains on the other side of the wall. Good night.